Some key engineering decisions are made in the design settings, and due to the various dissimilarities between the US and Canadian design settings, this tutorial will focus on the Canadian version. The first decision to make is which load standard to use for your structure. There are two choices: a low-rise method and a more general method for medium to high-rise structures. The low-rise option will benefit the designer by giving a slightly less conservative design, but is limited to single roof blocks. In order to use figure I-7, the structure should be less than 20 meters in height, as well as to have a height-to-width ratio of 0.5 or less. However, as per commentary I-26, a height-to-width ratio of 1 or less is permissible, and Shearwall will issue a warning saying that the former case is met. In the case where the height-to-width ratio is greater than 1, Shearwalls won't allow to use the low-rise figure. The all-heights method is more flexible, allowing the entry of any building shape, thus multiple roof blocks. Shearwalls version 9.2 does not allow the use of the low-rise figure when multiple roof blocks are used, such as in tutorial 2, even though the height-to-width ratio is satisfied. For this example, a two-story structure with one roof block is used to demonstrate various effects of the settings, therefore the low-rise method will be used. As for the seismic design, an equivalent static method suitable for almost all wood structures is used. Back to the design procedures in the settings menu, you can decide to include a deflection analysis. Activating this option enables the distribution of loads to be done using stiffness rather than capacity. An important component of the deflection equation is the hold-down deflection. Therefore, it is important to have the correct settings for the hold-downs to include in the deflection analysis. The hold-down menu is available by selecting the hold-downs tab in the main settings menu. This section is divided into two main sections, which one deals with the hold-down forces, and the second one deals with the displacement dA for deflection. The Override Hold-Down Properties for section allows the user to enter specific values of displacement and shrinkage for the hold-downs when the options are activated. However, note that if the displacement component is not known in the hold-down database, then the value of displacement shown here will be used, hence why it's not grayed out by default like shrinkage. The hold-down database can be viewed by exiting the settings menu and selecting the hold-down data bar. The original database can be edited, or a new hold-down can be created. Back to the hold-down settings. The section Wood Properties and Construction Details deals with default lengths subjected to shrinkage, as well as the displacement due to the wood crushing at the compression end of the wall segment, plus the extra displacement due to miscuts, gaps, and others. These parameters are accounted for in the deflection and shrinkage of the structure. A new Shearwalls feature found in the design settings is the worst-case design, also referred to as the envelope design. This feature is handy when many unknowns are left for the wall's parameters, and in comparison to earlier versions where Shearwalls would design separate walls for wind design, seismic design, flexible distribution, rigid distribution, and both force directions, thus resulting in a possibility of 8 design walls for each physical wall in the structure. This option allows the user to cover the whole envelope of possible diaphragm rigidities. When the setting is selected, the program first designs a wall for flexible diaphragm forces, and then, when designing for rigid forces, if they are lower, the program simply uses the wall designed with the flexible force. If they are higher than the flexible force, it replaces the wall designed for flexible forces with the one designed for rigid forces. Then for deflection-based intra-shear lines distribution, the wall is then processed again for flexible forces on the next iteration. To illustrate this, we will deactivate the option, leave the wall parameters of our two-story structure as unknown, So all the exterior walls have unknown properties, as well as for the interior shear wall. Prior to running the design, it is necessary to generate the loads. The loads will be generated for both wind and seismic. This Shearwalls warning is to let the user know that the height to width ratio is between 0.5 and 1. Therefore, wind loads are still generated and we can proceed with the design. We can see the shear wall schedule by going to Go to Table, Structural Data, and Sheathing and Framing Materials. Here it is possible to see 5 different wall groups. The parameters varied are the sheathing thickness and edge nailing. We will now rerun our design using the worst case envelope design. Following the rerun of the design, it can be seen that only 3 wall groups are used, which in turn reduces the likelihood of construction error on site. As a result of this implementation, in the shear result, Shearwalls now displays which case was critical to the selection of the wall. This can be seen by selecting the seismic shear tables by Go to Table, Seismic Design, Flexible Diaphragm Design, and Shear Results. As it can be seen beside the ratio of the applied force to the shear wall capacity, the letter W is displayed indicating that the wind case was critical to the design. Similarly, the letter S would be printed beside the response ratio in the wind design tables if the critical case was seismic for the design of the wall. This design setting is set by default to be checked. However, the setting will automatically be disabled if you have not chosen the design for both rigid and flexible diaphragms in the structure input. This option in the structure input form is available to give the option to the user. However, if a rigid analysis were to yield 5% on one line and 95% to another, while the flexible analysis is found to be 50-50, the engineer should probably design for the larger of the 2 loads for the individual walls. Therefore, engineering judgment shall be applied when deciding to design for only one diaphragm case. When designing shear walls, there are limitations to the height to width ratios based on the materials. This limit is 3.5 to 1 for wood shear walls. If a wall's segment height to width ratio exceeds that limit, it is not considered to contribute to shear resistance in the calculations of the design. In order to illustrate this, we will change the shear wall rigidity per unit length to use shear wall capacity to approximate rigidity. The reason for this is that sometimes when distributing based on deflection, even if the option is activated, no load may still be attributed to the segment. For example, looking at wall line A on level 1, it is possible to see that the 2 shear wall end segments are very small and exceed the height to width aspect ratio. Therefore, no load should be attributed to those segments. We will now rerun the design with the option unchecked and go to Flexible Wind Shear Results. As it can be seen, segments 1 and 5 have been attributed no load. Now, if we activate the option and rerun the design, segments 1 and 5 will now have some load attributed to it. One application to disregard shear wall height to width limitations is to implement proprietary non-wood-based shear-resisting elements. Do this with caution. The next section, Material Restrictions for Anchorages, offers the user three options. The first option, Override Hold-Down Selection to Achieve Design, allows a choice of all material in the design of shear walls. It will specify hold-downs if the required shear capacity of a wall cannot be achieved without them using the wall materials selected by the user. If wall materials are selected that always requires hold-downs, the hold-down setting automatically changes to hold-downs on all segments. The second option, Restrict Materials because of Anchorage Selection, restricts the materials available for the design of shear walls to those that can achieve the required shear resistance with the hold-down configuration specified by the user. If the user leaves a wall material selection unknown, the program still limits the wall design in accordance with the material restrictions. The third option, Restrict Materials but Override when unknown, restricts the material as in the previous option. However, with the following exception, the program will not limit this parameter in its design of shear walls. It will override the user-specified hold-down configuration to achieve the required shear capacity rather than limit the unknown parameter. The all shear walls on shear lines have the same materials option when not activated allows the user to have dissimilar material on the same shear line. For example, looking in the walls view, it is possible to see that shear line 2 contains two segments, one that is inside the structure and the other on the perimeter. Wall 2-1 is designed as an interior shear wall with gypsum on both sides, while wall 2-2 is designed as an exterior shear wall. Looking at the wind flexible shear results, it can be seen on both levels that wall 2-1 and wall 2-2 have different wall groups. Going to the shear wall schedule, it is possible to see that wall group 1 and 2 are wood-based shear walls, while wall group 3 is a gypsum-based shear wall. Now, if we activate the all shear walls on shear lines have same materials, the software issues a warning that materials along shear lines will be modified to have the same material. Now, wall 2-1 is changed to an exterior wall with hold-downs. Activating the Disable Gypsum Contribution for Seismic Design and Wind Design will disable the contribution from gypsum for both wind and seismic forces. If no gypsum is present, as it is now the case, while the option is activated for seismic and that an RD of 2 has been entered in the site information menu, the software will issue a warning. We will activate the option, enter a value of 2 for RD in the site information, and then regenerate the loads. By selecting yes, the values of RD will change back to 3. The hold down forces based on section allows the user to choose whether the hold downs are based on the shear wall capacity or the applied load. Similarly, the drag strut forces based on section allows the user to choose whether the drag struts are based on the shear wall capacity or the applied load. However, for both the drag strut and the hold downs, as per the following clause, even though the option applied loads is chosen, the software will override the applied loads by shear wall capacity for seismic discontinuities. By default, both forces will be based on the loads distributed to the shear lines. Certain situations require hold downs and drag struts to be designed based on the strength of the shear wall in order to ensure the drag struts and hold downs do not fail before the shear wall fails. And so selecting the shear wall capacity would be appropriate then. The user has the option of defining maximum shear line for the plan and elevation. A shear line consists of one or more parallel shear walls that act as one to resist an applied shear load. Walls can be on the same shear line as long as they are separated by no more than the maximum shear wall plan offset if on the same level, and the maximum shear wall elevation offset if they are on different levels. None of the design codes implemented in the program recommend a shear line offset. However, a default offset was implemented to provide tolerance for automatic shear line generation. There are two common approaches to determine a shear wall's relative rigidity derived from deflection, based on its capacity or its stiffness. Shear wall's rigidity is important when distributing loads to shear lines using a rigid diaphragm analysis. The capacity method is much easier to calculate and is an acceptable alternative to more rigorous stiffness deflection method. The shear wall deflection method calculates rigidity based on the stiffness of the segments derived from the four-term deflection equation. This uses a rigorous analysis that includes bending deflection, sheathing shear deflection, and nail and hold-down slippage to determine the deflection, the inverse of which is stiffness. Furthermore, there is a checkbox to distribute forces to wall segments based on rigidity, which distributes the forces to each wall segment within a shear line once the forces are distributed to the shear line based on wall rigidity. The method used to distribute loads to shear lines will be the same method used to distribute loads within shear lines. You can also decide to assume shear walls have equal rigidity, which assumes that all shear walls have the same rigidity per unit length, so the rigidity of any shear line is proportional to its length. Use this approach with caution. Manually assigning the relative rigidities is also possible. When you select this option, the default value is 1 for all shear walls, which means all shear walls have equal rigidity. This method may be useful when trying to include proprietary walls in your design. Try distributing the loads using the deflection first, then change to manual, which opens up the relative rigidity per unit length in the wall input window. Then modify the appropriate relative rigidities to suit the proprietary product. You may need to disregard shear wall's height to width limitations. The height restriction for wind loads section allows the user to choose the height of the structures when applying the restrictions regarding the applicability of figures I7 and I15. The choices for the height to use for these restrictions are the mean roof height, which is halfway from eave to ridge, the ridge height, and the eave height of the uppermost story below the ridge. A choice has been added due to the fact that there are currently no other method available for roof block structures and shear walls other than to use the all heights method intended for flat roof structures, which may not be the case for the structure the user is designing. This allows the user to apply to his or her discretion what reference height should be used. The service conditions applies to all walls on the structure. Shear walls applies the service condition factors to the nail withdrawal calculation for components and cladding, as well as determines the amount of shrinkage for the purpose of calculating deflections. When the deflection analysis is not included, the options are season or unseason and dry or wet for in-service. If the deflection analysis is included, then the program allows the user to enter the precise moisture content for both cases. 15% is also used to define wet in-service conditions. This concludes the tutorial about the design settings in the Canadian version.